Ever wondered how your computer finds a specific file among thousands in a split second? It's all thanks to searching techniques in data structures. These techniques are fundamental operations that allow us to find specific elements within a collection efficiently. Different data structures offer various searching techniques, each with its own advantages and disadvantages. In the next few minutes, we'll give you a brief overview of some of the most common techniques. These include linear search, binary search, hashing, and tree search. Linear search is simple and easy, checking each element one by one. Binary search is a bit more complex, dividing and conquering sorted collections. Hashing uses a hash function to map keys to values, while tree search involves traversing the nodes of a tree data structure. Each technique is unique and powerful in its own right. So, are you ready to dive in? Let's start with our first search technique, the linear search. Imagine you're looking for a book on a shelf, and you go through each book one by one. That's the idea behind linear search. Linear search, also known as sequential search, is the most straightforward approach to finding a specific element within a collection. It's a bit like playing hide-and-go-seek with your keys. You start from one end of the collection and examine each element one by one until you either find your target or run out of places to look. This method is versatile and can be employed on any type of sequential data structure, be it an array, a linked list, or a simple line of books on a shelf. However, its simplicity comes with a trade-off in efficiency. The time complexity of a linear search is expressed as ON, where N is the number of elements in the collection. In the worst-case scenario, you might have to look through every single element before finding your target. Or even worse, realize that it's not there at all. The main advantage of a linear search is its simplicity. It's incredibly easy to understand and implement, making it a great starting point for beginners in computer science. It doesn't require any specific ordering of the elements and works equally well on both sorted and unsorted data. However, when it comes to large collections, linear search starts to lose its charm. Its time complexity doesn't improve with the size of the collection, making it inefficient for larger data sets. If you're looking for a needle in a haystack, going through each straw one by one is not the best strategy. In summary, linear search is the equivalent of a trusty old hammer in your toolkit. It's simple, reliable, and works on just about anything. But like a hammer, it's not always the most efficient or elegant solution to every problem. While linear search is straightforward, it's not the most time efficient. Let's explore a faster approach, the binary search. If you're searching for a word in a dictionary, you don't start from the beginning, right? You open up somewhere in the middle and narrow down your search. That's binary search for you. Binary search is a true embodiment of the classic divide and conquer strategy. Instead of examining every nook and cranny, it zeroes in on its target by repeatedly dividing the search space in half. But there's a catch. For binary search to work, your data collection needs to be sorted. Imagine trying to find a word in a jumbled-up dictionary. Not so fun, right? Now let's talk about where you can use binary search. It's typically performed on sorted arrays and other ordered data structures. The reason is simple. When your data is sorted, you can make an educated guess about where your target might be and adjust your search accordingly. What about its time complexity? Binary search is a speed demon, especially when dealing with large collections. Its worst-case time complexity is O log n, where n is the number of elements in the collection. To put it simply, every time you double the size of your collection, the time it takes to find an element only increases by one step. That's quite the improvement from linear search's ON, isn't it? Of course, binary search isn't without its disadvantages. It requires the collection to be sorted initially, which might not always be the case. If your collection needs frequent updates, the additional overhead of keeping it sorted might make binary search less appealing. But for static, sorted collections, binary search is a top-notch choice. So to sum it up, binary search is a highly efficient searching technique, perfect for large sorted collections. It's like flipping through a well-organized dictionary, finding exactly what you need in a fraction of the time it would take to start from A and work your way down. Binary search is efficient, isn't it? But what if we could do even better? Enter hashing. Remember how you quickly find a contact on your phone by typing their name? That speed is thanks to hashing. Let's take a closer look at this digital wizardry. Hashing is a technique that uses a special function, known as a hash function, to map keys to values in a data structure called a hash table. Think of it like a magical librarian that knows exactly where each book is without having to look. The hash function generates an index for each key, which points directly to the location of its corresponding value in the hash table. So what kind of data structures can we use with hashing? Hashing is most commonly implemented using hash tables. These can be constructed using arrays or other data structures, depending on the specific requirements of the task at hand. Now let's talk about speed. Hashing is like the superhero of search operations. On average, hashing can perform search, insertion, and deletion operations in constant time. That's O(1), assuming a good hash function and minimal collisions. That's right, it's like a flash of lightning. But what about the advantages? Hashing is not just fast, it's also extremely versatile. It's suitable for large collections and dynamic data, making it a popular choice for tasks where quick access to data is a priority. However, every superhero has its kryptonite, and for hashing, its collisions. These occur when two keys are mapped to the same index by the hash function. This can degrade performance and complicate operations. Also, hashing relies heavily on a good hash function to distribute elements evenly across the hash table. It's not typically suitable for applications requiring ordered traversal of elements, as the order of elements depends on the hash function rather than the inherent order of the data. Hashing is blazing fast, but it's not always the best option. Sometimes a tree search is more suitable. Imagine a family tree. You start at the root and traverse through branches to find a specific member. That's the essence of tree search. Now let's delve deeper into this. Tree search is a method of finding a specific node or member in a tree data structure. It does so by navigating through the tree from the root node, following the branches until it locates the desired node. This technique is used on tree data structures such as binary search trees, BSTs, AVL trees, and red-black trees, to name a few. So how does it work? Well, in a binary search tree, for example, we begin at the root node. If the value we're searching for is less than the root, we traverse to the left child. If it's greater, we traverse to the right. This process continues until we either find our target or exhaust all possible nodes. When it comes to time complexity, tree search is quite efficient. On average, search operations in balanced trees like AVL trees and red-black trees have a time complexity of O log n. However, if the tree is not balanced, the worst-case scenario could be ON. So it's crucial to maintain a balanced tree for optimal performance. Now, let's consider the advantages of tree search. It offers efficient searching in ordered collections and is suitable for dynamic data. Furthermore, it's great for maintaining sorted collections. However, like all techniques, it does have its disadvantages. The primary one being the need for the tree to be balanced for optimal performance. This means that insertion and deletion operations may require rebalancing of the tree, which can add some complexity to the process. To sum it up, tree search provides an effective way of searching data, balancing out the benefits of the other techniques we've discussed. It's a powerful tool in the right circumstances, and with a solid understanding of its strengths and weaknesses, can be a significant asset in your data structure toolbox. Tree search is quite effective, balancing the benefits of the other techniques we've discussed. So, we've explored 4 key search techniques today. Linear search, with its simplicity, is great for small collections or unsorted data. Binary search, on the other hand, shines in its efficiency for large, sorted collections, dividing and conquering until it hits the target. Hashing, with its impressive average access time, is perfect for dynamic data and large collections, as long as a good hash function is in play. And let's not forget tree-based searching, which offers efficient searching in ordered collections and is a strong option for dynamic data, especially when the tree is balanced. Each of these methods has its own strengths and weaknesses, and understanding these can help you make the best choice for your specific scenario. Remember, the best search technique depends on your specific needs. So next time your computer finds a file in a split second, you'll know how it's done.